So the problem is, how do we get these optimal weights? We need some kind of criteria. And as I mentioned, it's basically a minimization process, an optimization process, where we set up the objective function, and the objective function will be the variance, the prediction variance, and we try to minimize that prediction variance subject to the constraint that the prediction has to be unbiased, so that on average the deviations between the predicted and the observed have to be 0. So you set this whole thing up and you solve it, and then you find the weights as the solution of that. And don't get scared, it's all matrix notation because I didn't want to write it out in full, but I'll explain what this is. This is a vector. So for each location S, we have a value of the weights. As you saw in the little illustration, each point has a different weight, so the weights are not constant. And we find this vector as the product of so the vector gives us the weight. Let's think of this in the context of the example. We had the yellow ball that we need to predict, and let's say we had 5 orange ones, right? So the vector has 5 weights, 1 for each of the orange locations. How do we get that? We get that by taking the inverse of the covariance matrix for the 5 orange points. So that is a 5 by 5 matrix. For each of the point pairs, we have a covariance that we get from plugging in our equation, as we'll see in a moment. So the inverse of that is also a 5 by 5 matrix. And then we multiply that by the covariances between each of the orange points and the yellow points. So that's, again, a 5-element vector. For each of the orange points, we have the distance between the orange point and the yellow point. We plug that into our covariance function. That gives us this C and S. So multiplying a 5 by 5 matrix with a 5 by 1 matrix gives us a 5 by 1 vector of weights. And this, I'll spare you the details if you want them. You can go at the references. It's a classic result that these weights are the minimum variance predictor weights for an unbiased predictor. If you want to do a nonlinear unbiased predictor, then it's a more complicated objective function for the optimization, but you can find the result in the same way. Now, there's a problem here in practice. 5 by 5 is no big deal, right? If you have 400 points, then this becomes a 400 by 400 matrix. In practice, therefore, it is almost never used in its full size. It could be, but it isn't. And why doesn't this matter too much? Because there's distance decay. And remember, the real power of the semi-variogram, or the spatial covariance, is in this distance band between 0 and the range. Once you're beyond the range, there is no more spatial autocorrelation. So for those pairs, really the covariance doesn't matter. So for all practical purposes, whether you take all 400 observations or say the closest 20, is not going to make a big difference. And in practice, therefore, you typically use a moving window to get these predictions, where you take the subset of all the data points, determined in some fashion. And again, here, there's a lot of art involved. Remember the other day I said Kriging is just like forecasting. Forecasting is part science and part art, because it's essentially combining information to come up with something for an observation that you don't observe yet in the case of forecasting, or where you can't be in that location in the case of spatial prediction. So some people are good at it, some people are not good at it. Okay? And a lot of this comes with experience. If you've ever been in the forecasting business, you very quickly throw your textbooks away, and a lot has to do with what works. And some of the theory works, but not all of the theory works. So it's the same in spatial prediction and spatial interpolation. And A lot of judgment is involved in not only picking the model for the variogram, but also how you get the parameters for that model. We've already had some sense of that with the choice of the bins, number of bins, width of the bins, take all the points, take subset of the points, take the variogram. All these will give you different C's to plug in here, and will, as a result, give you different weights and different predictions. So the predictor itself, then, is the combination. Remember, this is just the weights. The prediction is a linear weighted prediction, so we plug the weights in a weighted sum, and this is just a complicated way of writing sum over j, lambda j, yj, in that I have plugged in the result that we just had, and in matrix notation, this will be a row vector of weights multiplied by a column vector of observations. So 1 times 5 times 5 times 1 gives us a 1 by 1, a scalar, which is the predicted value for that location S. So this is the mathematics behind it. So what it boils down to is that you have to come up with these numbers to plug in here. And these numbers depend on the interpoint distances of the observed data points. These numbers in this small c depend on the distance between the observed points and the point that you want to predict. So all of these are things you can measure with your variogram function in hand. You just plug them in, you get the covariances, and you get them. Okay. Of course, it's not as simple as it sounds, because anytime you say we are estimating, then you just have a point estimate. But we just spend a lot of time discussing the difference between the first and the second moment. A point estimate is just dealing with the first moment, with on average. But how good is this point estimate? And of course, the quality of the point estimate will be reflected in the quality of the weights. And the quality of the weights will be reflected in the quality of the prediction. So the uncertainty in the estimation of the parameters of the variogram should be, strictly speaking, taken into account to get a sense for the uncertainty in your prediction. Sometimes it is, sometimes it isn't. Okay? This is something to keep in mind, because when your estimates, and you'll get some sense of this in the lab, when your estimates for the range and the sill and the nugget are no good, then of course your weights are no good and your predictions are no good. So that's a source of uncertainty. That is not the same as the second source of uncertainty that I'll talk about in a minute. So the result of this prediction thing is that you get this nice map. Now how do you actually get this map? I'm asking you, how would you get this map? Don't tell me I used geostatistical analyst and go click, click, click. Where do these colors come from? Yeah, but how do you get to the predicted value? There's no magic here. You have to come up with points. If you don't have points, you have no prediction. So ArcGIS puts a grid of points in this bounding box, and for every one of them comes up with a predicted value, and then puts that in this case in a raster and maps the raster. Or it can put it in a raster and map the contour lines in some fashion. But what's important to remember, and I know in the beginning, the first time you use these techniques, it's like magic. You know, there's this map, and I have colors everywhere. But, you know, I can give you another map based on the same variogram and the same parameters that looks very different from this map. Because all I have to do is space my points differently, and I will give you a different map. So this is very important, depending on what you're trying to do. The spacing of your grid points for which you get the predicted values is crucial for the representation of the result. It's not crucial for the result, because the result is always uses the same method. You get your point, you take the distance to the nearest points, you get the Kriging weights, and you get your prediction. Right? The question is, how many of these should you take? How far apart should they be? How do I represent them as the output of my exercise? And that gets us back to some of the ideas we talked about in the very beginning when we talked about mapping. The choice of colors, the choice of intervals, all these things can give you different impressions of the result. And that's something to keep in mind. How to lie with maps. Right?
In this case, your X and Y's for the existing house are really fixed, right? Instead of thinking of the grid one.
Yeah, well, this is a different example because I'm only predicting the residuals.
Okay.
Okay, there's no actual, well, actually, no, this is a trend surface. Yeah, it is the predicted values. So for every reference point, I have X and Y,
right,
which I stick into a trend surface. That gives me my predicted value. And then on the residuals of that, I use the Kriging to get the interpolated value. We'll do that in a minute. The exercise will walk you through exactly this one. But I thought your question was about, can we actually get predicted values for these points? And that is only if we have actual X variables for those points. So if these were houses,
right.
we would need actual house locations.
That's what
and we would need actual measures of square footage, number of rooms, size of the garage, and all this kind of stuff. So in that sense, you can't get a map like this.
right. So,
right?
because you have, in a sense, it's not a continuous.
It's
X,
not a
Y,
continuous.
you
Right,
have this.
right. So in order to get what you can do, and in fact this is one of the applications, is you can have, say, a city map with every single parcel, right? So every parcel becomes a dot. Now let's say you have 40,000 parcels and there were 1,000 transactions, or less than that, 4%, whatever. So on your transactions, you fit the model. And then for each of the parcels, you have the X variables, whatever they are, they have to be available. You stick them into the model to get a predicted value. Then you can make a map of the predicted sales price or predicted assessed value for every house in the city and use that for taxation.
So why were you saying that that's not considered a continuous surface, the predicted values?
Well, it is and it isn't. The continuous surface is to get you the covariance for the residuals. Okay? So conceptually, the mathematical model thinks of that as a continuum. In practice, to get a predicted value, see, there's the two parts, the mean, the large-scale trend, and the small-scale variation. The continuous surface is about the small-scale variation. The large-scale trend is about, in practice, can I come up with a prediction for the mean or not? It's the mean, right? So that's why trend surfaces are so popular, because in a trend surface, you don't have to know anything about these houses. You just have to know if a house was located here, this is how much it would cost. Because I have modeled the price of the house as a function purely of its latitude and longitude. And then the residual, which is where the spatial effect comes in. Now, if you reject that as a model, as anybody dealing with housing or real estate would, then you can still use the same approach. But in terms of getting the predicted value, you need to have the model for the mean. And in order to be able to predict the mean, you need to have observations on the variables in your model for the mean. Okay. So if you do something with soils, and say you're looking at the characteristics of the soils, you can predict characteristics at other sample points, provided that you have information on, say, everything except whatever, some pollutant, right? So you have some sample points where you measure pollutant and then say characteristics of the soil, You have other points where you have the characteristics of the soil, but not the pollutants. And so then you can, in your model for the mean, you can predict that. And then you use your model for the second moment of the spatial covariance to get a better prediction, in the sense of better precision prediction than just simply using the mean. That's what it's all about. So you might say, well, this is kind of a red herring, because in the mean they're all the same. Well, yes, but that's not what it's about. It's about the precision. And the precision is the variability around the mean. And for prediction purposes, precision is everything. The mean is not very meaningful, as I just said in the example I gave you. Just think about that, about the weather example. On average, you could be right, but it's the range around that average that matters. And in policy applications, this is also very important. If you try to, in a lot of impact analysis, you multiply, let's say, a pollution estimate by some dollar amount. And so if your range around your point estimate is very wide, you come up with nonsensical results. You can come up with things like between $1,000 and $10 million. That's meaningless. Whereas if you can get your precision better, get the range down, then you can come up with more meaningful economic interpretation or policy interpretation of the results. So this second moment is just as important, if not more important in this context, as the first moment. So this is one result. The second thing is the Kriging variance, and this is something maybe a little counterintuitive. Now, this has nothing to do with the variability because of the fact that you use an estimate. This is the variability because you exploit some structure of the covariance for the error terms. And the way I like to think of it is, if you don't know anything about the error structure, then the variance of your prediction will equal the variance of the process. That's as good as you can do. But because we are taking advantage of additional information, we are doing better. And so our actual prediction variance is smaller than the variance of the process. And again, we can go through the math, but I'll spare you this. This is the main result. This is a positive value. So your prediction variance is actually the original variance less something. So you have gained precision by using this information on the spatial covariance of the error terms. And that's what it's all about. So it's actually, from a statistical point, it's a fairly straightforward thing. You have a linear interpolator, which is simply a weighted average of your observed values. The key question is, what are the weights? So I want weights that give me an unbiased prediction, which is one criterion. And then among those, I want the weights that give me the smallest variance. And this variance, the gain in precision, we can get that from here. Now, obviously, when this starts to be very small, we're not gaining. And when is this going to be the case? When we get too far away from our sample locations. It's just like forecasting over time. Predict me the GNP 30 years from now. Well, you have no idea. It's going to be a huge wedge, right? But predict me the GNP for next quarter, you can be pretty much on target. Same thing here. So the gain in precision that we get decreases as we move further and further away from our sample points. Because once we are beyond the range for all practical purposes, there is no longer any gain from being spatially correlated because we're not. So then we're back to our reference variance, which is simply the variance of the process. And you can see this in this map of the prediction standard error, which is simply the square root of the variance. You see these dark colors as we're moving out, then it just goes up. Again, same comment as before. where does this come from? We have to have a grid of reference points. We predict for these reference points, and then we can map them, do contour lines, do all kinds of stuff that we might. Okay, so that's the principle. It's a linear predictor, it's unbiased, and it gets us a gain in variance. It gets us greater precision than just naive conditional expectation. There are two types of Kriging models. I talked about the variogram models, and then that was one distinction that we made earlier today. But then there are differences between the Kriging models depending on how much information we take into account. And for example, we saw that spatial variability was distinguished between large-scale variation, the trend, and small-scale variability. This trend, is this known? That's kind of an artificial situation. In practice, this never happens. You don't know what the mean is. But is it constant? So you simply have to estimate some kind of average, and then you can take the deviations from that average to work with. Or is it variable, like in our model for the trend surface? The mean is really the predicted value using just the x and y coordinates, which is going to be different in each location. So we now have a variable mean that we need to estimate, plus the variability around that mean for the small scale variation. Okay. So each of these is going to be a different kind of Kriging. And when you read the literature, you see these terms, and I'll just spend a minute on it as we go. A second consideration is, what is the dependent variable? So far, I haven't really said anything about that. And we've just taken it as being continuous, but it could also be discrete. And so then again, that's a very interesting case where you try to predict 0, 1 variables at locations that you do not observe. This is important in applications dealing, say, with toxicity or something like that, or risk surfaces. In what locations is the risk of a fire exceeding a particular level? And so you have observed fires and non-fires in different locations. You model the surface, and then out of this comes this risk map that tells you where the chances that there may be a fire are higher than some limit that you set. This is a common application. We haven't talked about this. This is called indicator Kriging, but it's a very common application of Kriging methods. And then another criterion to keep in mind when you do Kriging is, what are the targets? You know, we've dealt with point Kriging. There's also something called block Kriging, which gives you predicted values for spatial aggregates. And in block Kriging is just basically point Kriging, but with another step, because you start when you approximate the area by making it discrete in terms of points in the area. So you predict values for the points, and then you use those to, strictly speaking, integrate them over the area, but it could be a mean, it could be maximum, a minimum, whatever, but it is for the area. So if you want to know what is the pollution in a given county, you have your raster over the county, you get predicted values for as many points as you want, and then you summarize those, and that is the number for the county. That's block Kriging. And the reason you can do this is because of this continuity, this surface. So this is one handle on the, what we call the changes support, or the modifiable areal unit problem. As long as you can predict at this point level, you can aggregate any way you want. So you need a good model to be able to predict at the point level, but then whether you cut it as a county or an electoral district or some water control zone or floodplain, it really doesn't matter. And you can move, if you wish, between scales as long as you have this. I mean, it's not really moving between scales because you need additional information. And the additional information is to be able to predict at the point level behind whatever scale it is that you're using. And this is block Kriging. Okay. Let me show you a couple of pictures for these. Simple Kriging is nice for textbook derivations, but basically useless, sorry. It's the case where the mean is known, so you don't have to worry about it. You only deal with the variability in the error term. And this, again, is from one of the Esri manuals. On a line, it's not in 2D, it's in 1D. So the mean is this solid line, meaning you know it, and then you try to model the variability around. Ordinary Kriging is often a good approximation in practice. It's where you estimate the mean, so it's no longer unknown, but it's estimated, but it is constant. So it's the same mean throughout, and you only deal with deviations from this unknown mean. So we have them now as dashed points, meaning that it's estimated, but we're still concerned with the variability around a constant level. And then the case that is the most realistic and the most commonly used in practice is so-called universal Kriging, where now the mean incorporates the large-scale variation and changes with location. So if we use a trend surface, we have a different mean in each location. And so that must be estimated, the parameters must be estimated, and then we're back to our starting point for today, which models the variability in this random variable as a combination of large-scale variation in the mean and small-scale variation in the error term, which in practice will be done through the residuals. So then we get this nice little curve where we have this varying mean with location, and then we model the variability around the varying mean. That's universal Kriging. So in most cases in our applications, we'll use some form of universal